Good afternoon, guys. We're doing another lecture for the physics class from the Carlton Adler Ballack book, Principles of Radiographic Imaging in Art and Science. This is in support of the physics course, the radiation physics course at National General Hospital School of Health Sciences Radiologic Technology program. This one is chopped quite a bit because usually I drop in about 5 YouTube video links for this. And so if you're watching this one on YouTube, understand that I've pulled those out so that this one records as a video a little bit easier, and it's not going to be a pain in the butt to upload. So there's about 5 videos missing from this that I will put in a live lecture and on Schoology too. Those of you outside my X-ray program, I'll do my best to explain what's going on, but a lot of the context is in the embedded videos. So let's get into this. All right. Describe electromagnetic radiation. Well, yeah, that sounds simple, doesn't it? Wave-particle duality, explain that. That doesn't make any sense at all. Explore characteristics of waves, special case of electromagnetic waves. Introduce the wave equation and the Planck equation. Gain familiarity with the EMR spectrum. EMR stands for electromagnetic radiation. Sorry, nurses, you can use electronic health record rather than electronic medical record, because EMR as an acronym was already taken in the field of healthcare. James Clerk Maxwell, he beat you by about 200 years. So, sorry. Compare the properties of light to X-ray, what we're going to find as we explore how light behaves and what even is it. We're going to figure out that the way that electromagnetic radiation behaves is very different for very different types of electromagnetic. Light behaves differently than X-ray does, and X-ray behaves differently than light does. What's the same, what's different? So there are some similar parts from if you took a light photon and an X-ray photon, there would be similar behaviors, but there's also different behaviors. And so I break those down on back-to-back slides. And then we wrap up with the photoelectric effect with an emphasis on wave versus particle and conservation of energy. And I'll share with you the conservation of energy formula for the photoelectric effect and its author. Okay, so that introductory video was Richard Feynman, which again on this recorded lecture, again, this is me filling in context. Richard Feynman talked about moves on a chessboard and figuring out the rules to chess by just observing the chessboard. And that really is the game of physics. We watch nature and we watch different events, and then we try to figure out what's happening there. And so that was basically Newton publishing his first book, which we've already talked about at length, the laws of motion, Principia Mathematica. That was his book. And so he started looking at other things, because that's what scientists do. He got bored. He solved the equation for the moon. That's a pretty big lift. Solved the math, created a new branch of math, calculus, to make the calculation to solve for the orbit of the moon around the Earth. And then he said, okay, done with that. You guys can explore other things with the motion system that I created and the rules that I laid out. But I'm going to move on to something else. I'm going to try to figure out what the hell light is. So his second book was Optics, Treatise Optics, in which he looked at a glass of water. I don't know if he had soda straws or not, but you can definitely tell something is happening to the light. Because I could see two soda straws, one on the side of the glass and one going down into the glass, and those don't line up. And I know that a soda straw is a linear object, and it doesn't do a bend like that. So what the heck is happening? So hang on just a second. So what's happening with the image of the straw? And how is it that we're seeing it as two different straws, one magnified, one non-magnified, one kind of curved? Well, both of them a little bit curved once they enter the water. That is weird, isn't it? And so Newton pondered this, and he just finished his book on 3 laws of motion. The first one was inertia, which, if you recall, objects travel in a straight line path unless acted upon by external force. And so, I'm sorry, lost my train of thought. Yeah, inertia. So if light were a particle and it was changing direction because it was acting upon by force, then that would explain refraction, which is what he called this property of light. And we kept the name, but the explanation fell apart rather quickly. Okay, well, about 400 years later. That's part of the story. And so Newton totally thought light was made out of particles he called corpuscles. And he said they were changing direction going through the water. And so that explains the refractive effect of looking through a glass of water. Okay. Sorry, got a little tongue-tied there. Well, Newton was Newton. He was the Michael Jordan of physics. He had just shown the mathematics for the moon's orbit. Okay. And other astronomers were furiously applying it to the other, like Mars and Jupiter and Venus and things like that. And every time, they could predict those other orbits. So Newton was basically, he couldn't get anything wrong. That's how famous he was in physics. Well, there was a little known physicist, there was a Dutch physicist, Christian Huygens. And Huygens disagreed with Newton's premise that light was particles. Partially because Newton kind of half-assed that explanation, because accelerations imply forces, and Newton didn't explain what force was being applied to the light corpuscles. He just said they changed direction. So where's the force? So Huygens said, no, it's a wave. And it's a wave that travels at a specific velocity like waves do. And so, like water waves, light is dependent upon the medium through which it travels. And so air and water and glass are very different. And light has a different velocity in each of those. And so it slows down in water and glass, less so in air. And that's what's causing it to bend. And that's what causes refraction. Well, Huygens did not write a previous book where he solved the mathematical equation for the orbit of the moon. And so he was roundly dismissed. Newton's right, you're wrong. Go work on something else. And so Christian Huygens never got the credit he deserved. And then this is where I play the Veritasium video that proves Huygens was right. You can look it up. It's called the original double slit experiment if you're listening to this on YouTube. Okay, and so this is commentary, just light-hearted commentary on that video. Derek, the host of Veritasium, interviewed several people. One of them is a lady talking about auras. She said you're going to see a kaleidoscope effect when you look into, when you view the double slit experiment. And she was right. She was also right about auras. But you can't really see auras, not because it's too bright outside, it's because you don't see in the infrared spectrum. Each and every human being emits infrared energy or electromagnetic radiation if you're alive and you have a body temperature, you're emitting infrared radiation right now. Okay, you might think of it as body heat. That's your infrared emission. So if we look at you through a thermal imaging camera, which detects infrared radiation and then shifts it up into the visible light spectrum for display, then we can see your heat signature. Yes, your aura, technically. Okay? And then there was a guy in a yellow shirt, and he correctly described how vision worked. Okay? And so go back and watch the video again and pay attention to what they say about, he's asking them, what is light? Is it a wave or a particle? What exactly is light? And the guy in the yellow shirt, but is not really yellow, he said vision worked like this. The light comes into your eyes and it bounces, it comes from light sources, whatever those are. We'll get into that later. But then it bounces off other objects. And that's how we see those objects. And then it's also how we perceive the color of those objects. Those objects do not possess that color. So your seal blue scrubs that we make you wear here in this program, they're not really seal blue. Okay. The polymer dye that it's embedded in the fibers is absorbing all the other wavelengths of visible light except for that specific wavelength. And so, yeah, your seal blue scrubs are not blue. None of the clothing you are wearing it doesn't possess the color. The color is the wavelengths of light bouncing off of it. So I wonder if we could get an ultraviolet shirt, like a shirt that radiates ultraviolet colors. Allows I'm sure there are. We're just not aware of them because we don't usually look in the ultraviolet range. So this definition of how vision works and how light bounces and how objects don't possess color adequately explains glass. Clear glass is clear because it's allowing all light to pass right through it without absorbing any of it. And so you see it as clear or near invisible. Okay. But most objects have molecules that are absorbing part of the electromagnetic spectrum in the visible light range, and that's why they appear colors. And then black is absorption of all colors of light, and then white is reflection or refraction of all colors of light. All right, so the video was about this. Thomas Young's double slit experiment. He took a candle in a dark room, possibly a study, possibly a laboratory, whatever, and he took a card like a thin paperboard, like an index card or a cereal box. He didn't have a cereal box, but maybe an index card. And he cut 2 slits in the card. Now, if Newton's right, and light is made out of tiny particles, every time without fail. Okay. Sorry about that. All right. So if Light's particles, then they have inertia. They travel in straight lines until acted upon by external force, right? So the diagram on the left would be accurate. The light coming from the candle passes through either the top slit or the bottom slit, but there is nothing that is going to refract it. And so it's not going to change direction. It's going to continue with its inertial straight line path, and it's going to intersect the projection screen at either that top point or the bottom point. And so we'll get two bright bands on the projection screen if it's a particle. But that is not what he got. What he got was striped bands with just two slits. He got multiple striped bands. And for those of you in my physics class, I can actually, and I do this every year, I'm going to do the double slit experiment for you live, okay, with my red laser, and I have a double slit slide and you can order one on the internet. It's fairly easy to get a hold of. It's the same one Derek used in his video. Okay, he used sunlight, and so it kind of complicated what you see in the background as far as the interference pattern, because the different wavelengths of light show up in different areas, and so they kind of crowd out the dark bands. But I'm going to be using a single wavelength of light, just red light at 633 nanometers. That's a helium neon laser, by the way. And we are going to see the diagram. We are going to see the pattern of the diagram on the right, which means that there are interfering waves, overlapping waves of crests and troughs, where the light constructively or destructively interferes. So the bright spots and the dark bands in between them. Okay? But here's the thing. There's no way that that shows up if light is particles. So what does that mean, gang? That means Newton was wrong. That's what that means. Okay? So this is piece of proof number one, that light is waves. Okay? This is piece of proof number two. And yes, I did promise you there would be no calculus. No calculus that you have to actually calculate. Okay? And so I have taken 3 years of college calculus, or 3 semesters of college calculus and differential equations, and I've taken college physics 1 and 2. And so I can read this. I can translate it to English. These are Maxwell's equations. James Clerk Maxwell was trying to create a unified theory of electromagnetism. And so he started writing down the rules, okay? And then he derived the fourth equation. And so by combining the other ones. And so let me just translate. The top equation, the source of the electric field is the charge. That's pretty straightforward. What he's saying there is electrons and protons create the electric field. Pretty straightforward, okay? The next one down says the magnetic field doesn't have a source particle. See the zero? But it also says, another way to read it is the magnetic field doesn't have a source particle, so that means there's no monopoles. Anytime you have a north pole in a magnetic field, there is a south pole somewhere else. Okay? And so those of you who watched The Big Bang Theory might remember Sheldon Cooper kept trying to look for magnetic monopoles. He was trying to prove this second equation wrong. Yeah, that's a fool's errand. There are no magnetic monopoles. The magnetic field doesn't have a particle source. Okay? Not like the electron has got a negative charge. There is no north pole particle. There's no south pole particle. They exist together. You have a north-south pole magnetic field, or you don't have a north-south pole magnetic field. That's it. There's either a magnetic field present with a certain positive magnitude, or the magnetic field is 0, and there is no magnetic field. So you can't have just a North Pole. There's a South Pole somewhere, okay, at the other end of the magnetic field. All right, so the third equation is, okay, so that second equation is Gauss's law, okay? I believe the third equation is Oestrig's law. No, the third equation is Faraday's law. The fourth equation is a special variation of Oestrig's law. So the third equation says that the magnetic field magnitude, or I'm sorry, the electric field magnitude is determined by the change in the magnetic field. So if the magnetic field changes, it creates an electric field magnitude. The fourth equation says the opposite. The fourth equation is Oestrig's law. Magnetic fields and magnitudes in the magnetic field are the result of changes in the electric field. Okay, but there's something very special about this fourth equation. This fourth equation is in the form of a wave, a sinusoidal wave. Okay, coupled with the third equation, it creates a double sinusoidal wave. Okay, and the term for the speed of the wave is in that fourth equation. You see I guess that would be script U naught and script and epsilon naught. That's the magnetic permeability of free space and the electrical permeability of free space. Those are constants. They've been measured in laboratory. You multiply those two terms together and you get the speed of the magnetic wave. When Maxwell solved for the speed of the magnetic wave, he dropped his chalk or his pen or whatever, because just before him, I don't know if it was 5 years, 10 years, but it was in the recent past, someone had done an experiment. I forget the man's name, but he had used a wheel with a hole in it and a very bright light and a mirror in another tower. So this was in a tower, and he rotated the wheel, and the wheel had a hole in it. And he rotated the wheel at a certain speed, so he knew the speed that the hole would show up. And then he had a mirror in a tower placed about 5 miles away. And so he knew that the mirror was 5 miles away, and he could measure the delay in seeing the flash of the mirror from the rotating wheel, where the hole in the wheel revealed the light source. And so with this experiment, he was able to conduct the speed of light across 5 miles and back. So a 10-mile distance. The number he came up with was very, very close to 3 times 10 to the 8th. Okay, which is also what Maxwell solved for when he wasn't even looking for the speed of light. It just popped out of this fourth equation that U naught epsilon naught, that's multiplied to the derivative of the electric field. That astounded him, made him drop his chalk or his pen, because he discovered something new. He was only trying to figure out how electricity and magnetism were related, but what he ended up doing was proving that light was an electromagnetic wave. Okay? And so that's when people started doubting Newton and believing Huygens, is when Maxwell showed up. So this is proof number 2 that electromagnetic radiation is a wave. Proof number 1 was Thomas Young's double slit experiment. This was an idea on a chalkboard, but no one had ever proven the wave quality of light until Thomas Young. People had Huygens theorized it, but didn't have the mathematics. Maxwell used Newton's calculus to prove Newton wrong. And so people abandoned corpuscles and started thinking about light as waves. This is the three-dimensional model of what that fourth equation solves for. Okay? And so what we have here is the red. You can think of the red as the z-axis of the photon. That's the direction of travel. The pink would be our x-axis, and the magnetic field is oscillating along the x-axis. And then 90 degrees opposed to that, the electric field is oscillating along the y-axis. And so those are symmetric sinusoidal waves, and they are paired. When you get a crest one way, you get a crest the other way in the electric field. When you get a trough, you get a trough in the magnetic field. And so they're paired exactly, and they kind of look like butterflies. Yeah, I see that now. But so this was Maxwell, like, graphed this out in 3D, which was amazing for just. Yeah, this was early 1800s, like 1820s, 1830s. I forget the exact date. But this is the first picture of a photon, effectively, or the first illustration of a photon, where and we really can't take a picture of the photon, so this is the best we got. This is how we represent a photon, even to this day. So that's pretty good for just a math formula in the early 1800s. Pretty good. Yeah, James Clerk Maxwell, off the charts. Well done, sir. So, and then the speed of the direction in the red arrow is 3 times 10 to the 8th. Okay, and so we end up with electromagnetic radiation, these tiny little ripples of the electric field and the magnetic field going out through space along the z-axis, and these oscillations and little ripples, and it's energy. We figured out that it's energy later. That's coming up in the story. That's coming up by the end of the PowerPoint. Electromagnetic radiation is energy, and it's energy in motion. It's always, you don't ever stop a photon. You can't slow it down, and recently physicists have slowed it down to ridiculously slow, and they were able to image it with a high-speed photon, and you can actually see the photon traveling through whatever medium they dreamed up to slow it down as much as they could. Coupled with a modern high-speed camera, you can actually see the bolus of light travel through whatever it is they do. It's pretty cool. Look it up on YouTube. It's awesome. So remember how we said waves? That was the part Huygens got wrong. He said waves travel through a medium. It turns out electromagnetic waves don't even need a medium. They can propagate through the vacuum of space too. They can propagate through the vacuum of the X-ray tube. Thank goodness, because we need a vacuum so that the electrons don't collide into other things. EMR exhibits wave-particle duality. No, wait a second. I thought we just said there's 2 pieces of proof there that it's waves. So what's this about particles? How come we didn't abandon particles in corpuscles? I thought you just said we proved Newton's wrong. Yeah, there's a twist coming. Just wait. Just wait. So it's energy, but particles imply matter. So it's both energy and matter? Yeah, that's the screwy part. Okay. Doesn't make any sense. It's both energy and matter. What? Okay, so it's responsible for excitation and ionization. We figured that out after James Clerk Maxwell and Thomas Young. And the energies determine the behavior of the photons. They behave differently if they have high energy versus low energy. And so here's the entire spectrum, and you can see low energies are over on the left-hand side of this chart. Visible light is just about in the middle, a little bit to the right of the middle. And then higher energy photons like X-rays are closer to the right hand side of the spectrum. Okay, and so the order that I learned is radio, microwave, infrared, Roy G. Biv, that is visible light, ultraviolet, X-ray, gamma ray, and cosmic ray. Now, since that time, we've actually learned cosmic rays are high-speed electrons and protons and other things, neutrinos and other quantum particles, not necessarily photons. So, but they're traveling at such a high rate of speed that they start to look like photons. So they're kind of misnamed. All right, so wave theory. Waves are disturbances in a medium unless you don't need a medium, like electromagnetic waves. So the waves that you might be familiar with are ocean waves, sound waves, things of that nature. You can tie a length of rope to a doorknob and whip your hand up and grab the other end of the rope and jigger your hand up and down, and you can create a wave. Okay. If you time it just right, you can create a nice standing wave. Okay. Guitar strings form half waves when you pluck them. Waves have parts to them, and this is where I usually embed another video about properties of waves. So the parts are the crests and the troughs. Those are the hills and the valleys of the wave. Amplitudes, which is how high is the hill or how deep is the trough. Nodes are where the wave is undulating. Usually nodes and antinodes are for standing waves, and where you get a lot of vibration versus where you get very little vibration. Typically the antinodes are the halfway points between the crests and the troughs in a standing wave. The amplitude, so I already explained the amplitude. The wavelength of the wave is the distance required to include one whole crest and one whole trough. The frequency is if the wave is moving past you, how many full wavelengths pass in 1 second. And frequency is measured in hertz. Hertz was among, I didn't mention him in the history of X-ray, but he was also working with Crookes tubes and Geissler tubes and all that stuff. And he was very, very close to discovering X-rays as well. And so frequency, named after Hertz, it's cycles per second. And what is a cycle? It's a wave. A crest and a trough is a cycle. Okay? And so you can kind of think about wavelength as meters per cycle, and then frequency is cycles per second. And those are both fractions. So if you multiply those fractions together, you would end up with meters per second. Very good. And so electromagnetic radiation, it has wavelength, it has frequency, and it has energy. Now we'll come to the equation for the energy of electromagnetic wave in just a couple of slides. But the general wave equation is the velocity of any wave is just its wavelength times its frequency. But for electromagnetic waves, we already know the velocity of the wave. It's constant. It's 3 times 10 to the 8th meters per second. Yes, I know, I just said it slows down in glass and water. We ignore that for X-ray curriculum. Okay, we don't care about refraction. Refraction, that's an upcoming slide, doesn't happen with X-ray. And so for us, the X-ray photon always travels at 3 times 10 to the 8th meters per second. And it also makes things easier. And as Einstein said in special relativity, if you don't treat light like it always travels at 3 times 10 to the 8th meters per second, then every other measurement you make in physics breaks down and becomes unusable information. And basically inaccurate information. So the speed of light has to be constant, so our measurements mean things. And so that's the assumption that we have to make in order for all of the rest of physics to make sense. And when you think about it, we use our eyeballs in just about every measurement we make. We're reading a gauge or a ruler or some such thing. And so we're using our eyes, so therefore we're using light to take these measurements. If light's not traveling at a constant speed throughout the measurement process, then the measurement doesn't mean anything. It's a blind shot in the dark, really, because light could change speed and then that would change the measurement. You see what I'm saying? So light it has to have a constant speed, otherwise nothing makes sense. Okay. So again, V equals F times lambda, where lambda is the frequency, or lambda is the wavelength. Script F is the frequency, not capital F, script F. Okay. Little v for velocity. And then that funny symbol in the parentheses, that is the Greek letter lambda. It's the ancient Greek's equivalent of L. Why L? Because length, that's why. Okay. So wavelength, we couldn't use L because that's liters. In the metrics, this little l is already used as liters, and so we had to use lambda because we still wanted to think about L, but not exactly the same as liters. So the wave equation, the general wave equation, waves don't have to travel at a constant speed, but they do have to obey that formula. The product of the frequency and the wavelength is the velocity of the wave. But for light and all other forms of electromagnetic radiation, the velocity is a known value. It's a constant. And so we call that, it's little c. Whenever you see little c in physics, that's the speed of light. That's 3 times 10 to the 8th meters per second. Okay? So, and this solves. They apply this to electromagnetic radiation, and it works. We know the frequency and the wavelength for red light. We know the frequency and the wavelength for a lot of the electromagnetic spectrum. We know X-rays are between, they're right around, the frequency is right around 1 times 10 to the minus 18th. Or no, 10 to the 18th, not minus 18th, 10 to the 18th hertz. Okay. So 3 different ways, that we know it's a wave. It satisfies the wave equation, frequency times wavelength does yield the speed of light for every photon that we measure of specific wavelength and specific frequency. It satisfies Maxwell's equations and fits Maxwell's model of the electromagnetic wave. And Thomas Young provided proof for the wave quality of light and electromagnetic radiation by performing the double slit experiment. Okay. Oh, God. Yeah. I think we got to listen to this guy. He might know what he's talking about. All right. So definitely not a particle. Newton was wrong. Until this guy shows up. And yeah, you know what? Sometimes light does in fact behave like a particle. And we're actually trying to unravel this idea. This is a shortcut. So This is the conservation of energy formula for the photoelectric effect. And Albert Einstein won the Nobel Prize in physics for discovering the photoelectric effect, I think in 1920. You can look that up if you want to. And so the photoelectric effect basically says that a light photon collides with an electron that's orbiting in an atom in a Bohr model and provides the energy to knock the electron out of its stable orbit. Okay? And so he borrowed several ideas: kinetic energy from Newton, treating the electron as a particle, which works out just great because that's what we want to do too. HF is borrowed from the Planck equation for energy, and then the work function, which is that other symbol. So you might recognize HF on the left hand side, and then there's that's a Greek letter phi. That's the binding energy for the electron shell that the electron happens to be in. So if a photon comes along, it can give the electron the binding energy, releasing it from the atom, and then the electron wanders off with a specific velocity, which is the remainder of the photon energy. The photon disappears. It's completely absorbed by the electron. Some of the energy is spent to free it from its orbital binding energy. And then the rest of the energy manifests as a kinetic energy of the photoelectron. Okay? And so Planck called them quanta. I'm not sure when we started adopting the nomenclature of photons. We stopped using quanta and we started calling them photons. I don't know when that happened and who came up with the name photons, but quanta and photons are the same thing. It's that picture that I showed you. Okay? It's a little ripple of electromagnetic energy. And so, yeah, he kind of said, well, Newton was wrong in his explanation of refraction, but there are certain circumstances where light and electromagnetic waves behave as if they were particles, because it's like they collide with the electrons in the atom and ionize them. Okay, and then this is where I would play another video. How can a wave act like a particle and collide with an electron? And so I've got a video of a wave machine hitting a model boat and capsizing it. And so that's what you miss, and I'll play that in class if you're in my physics course. And so it turns out that once you get past a certain energy and you have high energy photons, like X-rays, they can interact with electrons bound to the atoms that they're passing by. So if the photon intersects an atom and it has high enough energy, then it could ionize that atom. Okay? And so Einstein discovered what would be the first ionization reaction, of which there's about 4. Okay? Short on his heels was Arthur Compton, and Arthur Compton figured out Compton scatter. Right? And then there was Max Planck. Now, Max Planck was before Einstein. Einstein used Max Planck's formula in his photoelectric effect formula. And so Max Planck was doing a study for the German government because electricity and Edison's DC electric circuit and Siemens was working on electricity and the electric grid for Germany, and Max Planck was a physics professor at university in Germany. I forget which university he was at. Um, but the German government came to him and said, look, Mr. Siemens, this businessman, we're trying to run electric power and to have electricity in every home and electric lights and electric street lamps. But for the street lamps, we want to know how much electricity we actually have to run, because electricity is expensive. It's expensive to generate, and so we want to know how much electricity is necessary, that is, how much energy is necessary to power the light bulbs and the street lamps, because we don't want to send too much and we don't want to send too little. We want optimum energies. And so Max Planck got on it. He was a pretty bright guy. He was up on all the latest scientific literature. And what he found is light photons travel in discrete packets of energy, and there were gaps. It wasn't a continuum of energy. It was finite quantities of energy. And so he published this as the equation E equals HF, which is the Planck equation for electromagnetic waves. And so the energy that a photon possesses is equal to Planck's constant, which is that number there at the bottom, times the frequency of the photon. Okay? And so when light emits energy, it does so in tiny little chunks, which Planck called quanta, okay? Which means tiny little finite packets of energy, not a continuous stream of energy, okay? And Einstein took this and said, okay, what if these tiny little packets of energy hit atoms? Because Bohr said that the electrons were bound to the atoms by discrete quantities of energy. So what if we take photons that have the same energy as the binding energy, or slightly more energy than binding energy? Is that going to release the electron from the atom? And that's basically what the photoelectric effect says happens. And lo and behold, that was proven by experiment. I think they used sodium metal and light photons from a flashlight, and they were able to conduct electricity by just shining light on sodium metal. And so the photoelectric effect and its second cousin, the photovoltaic effect, led to solar panels, but also led us to an understanding of why the phosphors were glowing from the X-ray photons in the X-ray tube. So the photoelectric effect kind of opened up a lot of doors as far as understanding of both light and X-ray and other electromagnetic waves. Okay, and so the modern understanding, there's variance about the behavior of photons according to the energies of the Planck equations. And so light has lower frequencies and lower energies than X radiation. And so we can see reflection and refraction and diffraction with light. And I give examples there. But light doesn't typically have enough energy, with the exception of sodium, to ionize atoms. Okay. Now, X-ray behaves quite a bit differently than light. First of all, we can't see X-rays. Okay. We can tell where they've been by photoelectric effect. When we see photoelectric effect and the evidence of photoelectric effect, then we know that X-rays have been there. But we can't see X-rays like we can light. And so X-rays don't reflect. X-ray telescopes don't, they kind of reflect, but it's more like a deliberate Compton scatter with a very specific angle. And that's all I'm going to say. They don't refract. And I don't think we've ever run a double slit experiment with X radiation. I'll have to look that up, but I don't think it does. And because of Compton scatter, I'm not sure we're going to see anything meaningful with a double slit experiment. I guess you would use lead and cut some slits into lead and have them very close together. But I don't know if anyone's ever done that experimentally. So for now, in our understanding, X-rays do not diffract or interfere. But do they ionize atoms? Yes, prolifically. X radiation and radiation energies higher than X radiation definitely ionize atoms. All right, so what does all EMR do if it doesn't all reflect and refract and diffract or interfere? Well, transmit, attenuate, and absorb. So you can see on the left picture various pieces of glass. One of them is clear or lucent. The other one is frosted, so semi-lucent. Okay. And then one of them is painted black, so opaque. Okay. And so you can see pretty much all the light photons get through the transparent glass or the lucent glass. Only a fraction of the light photons get through the frosted glass, and then the glass we painted black, the black paint is going to absorb all the photons. Well, that's kind of like X-ray contrast. So the air around this patient's hand is not absorbing any photons. It's radiolucent. The soft tissue is stopping some, but not all the photons. And so we can say that the X-ray is attenuated. And the bones too. The bones stop quite a few X-ray photons, but not all of them. But the lead marker, that little L with the KCS, the lead is absorbing almost all the X-ray photons. That's why it's showing up white. Okay. And black things are black because you're not getting any photons bounce off them. The material is not black, it's just absorbing all the photons, and so you perceive it as black because you're not getting any photons entering your eyeballs. Okay. Sorry if that breaks your brain, but that is how your eyes work, and that's how colors work. So white is a combination of all the colors. Newton did get that part right. You can separate the colors of light by a prism. And so Newton was the one who explained where rainbows come from. Yes. Okay. X-rays are a penetrating and invisible form of electromagnetic radiation. They are electrically neutral, so they don't have a charge. Photons are not charged. Polyenergetic or heterogeneous energies, and so X-ray photons are a range of energies, light photons are a range of energies. The entire electromagnetic spectrum is a range of energies, and so taking a photon and measuring its energy and then taking another photon at random from any light or X-ray source, you're going to get a different energy. It's highly probable you'll get, now you might get the same one, but there's a wide variety of energies in shining a flashlight, but also in an X-ray beam exposure. Okay. They travel in straight lines, but of course you already knew that because you've already taken X-rays and there's a targeting crosshair, and that's for a reason, because that is the direction we're letting X-rays escape the X-ray tube. And so X-rays travel in straight lines, they do not divert. They also travel at the speed of light, little c, 3 times 10 to the 8th meters per second. X-rays can ionize matter, they can cause certain materials to fluoresce, and they cannot be focused by a lens, which is a special type of refraction. All right, and so that's a lot of properties. I'm not finished. X-rays can also affect photographic film. They can produce chemical and biological changes in matter, especially tissue. Okay, and they do so by ionization and excitation. They can also produce secondary and scatter radiation. Now, of this list, I think the only ones Rankin did not discover are the last 2 bullet points. And so he was pretty thorough in his research of whatever X-ray was. He learned, so affect photographic film all the way back to the previous slide, and the end of the list, or the beginning of the list, we learned all that from Rankin's original paper. Okay, we figured out the chemical and biological changes and the ionization and the secondary and scatter radiation from people that followed Rankin, like Arthur Compton and Albert Einstein, okay, among others. Okay. And so, what the heck is ionization? Well, ionization is the creation of ions. What's an ion? An ion is an atom with an imbalance of charges, or, loosely speaking, a free electron that's not tethered to an atom is a negative ion as well. And so there's positive and negative ions, and they're usually formed in pairs because matter doesn't like ions. It's non-stable, it's highly reactive, and they usually try to either borrow or steal an electron from somewhere else to balance themselves back out. It really bugs an atom to be an ion, and so it's a temporary condition. Okay? Except for acids, something about acids, you get ions readily available. Okay? That's an ionic bond has broken apart in water. So photons that interact with atoms have high enough energy that they can ionize the atom. They can deposit that energy to one of the orbital electrons and allow that electron to go free. So the 2 primary forms of ionization in the X-ray curriculum are the photoelectric effect and Compton scatter. And I think I explained those on the upcoming slides. So from left to right, we have a photon coming in and hitting the yellowish green atom that has 6 electrons and 6 protons in its nucleus. So it's got a balance of charges. After it motivates that 1 electron to leave, now there's only 5 electrons, but there's 6 protons still in the nucleus. And so now you've created a carbon atom, a positive ion of carbon. And that means it's missing at least 1 electron. Okay? So you can have ions that are +1, +2, +3. I think that's close to the limit. There might be one that forms a +4. That might be iron forms a +4. So, but as far as I know, ionization states beyond +4 are very, very rare. All right, so let's walk through the photoelectric interaction. Part 1, the X-ray photon, there it is, HF on the left-hand side, possesses some energy and comes into the atom. Remember, the Bohr diagram is not a physical model, it's an theoretical energy model. And so electrons in the first shell, the K shell, have the highest binding energy. But when a photon has more energy than that binding energy, it can knock that electron loose. The electron also, with the remainder of the photon energy, that is the difference between the photon energy and the binding energy, is the energy of the kinetic energy of the electron. And so the photoelectron has a very, very tiny mass, and so it acquires a velocity when yes, it was in orbit around an atom, but it was basically stationary versus the photoelectron's high velocity. Okay? So what do you leave behind? What do you create? You create an ion pair. The photoelectron is a negative ion, and it will probably seek out a valence vacancy at a nearby available atom or molecule. And that, if that's biologic tissue, then that could cause damage. It's an unwanted chemical reaction. The other thing you get is an atom with a temporary K-shell vacancy. Now that vacancy, remember, the electrons in the outer shells are in a higher energy state than the electrons in the lower shells. And so nature doesn't like that vacancy, and you get one of the outer shell electrons cascades down like a series of small waterfalls to fill the vacancy, because the electron doesn't want to stay at a higher energy state. When that cascade happens, the conservation of energy says the difference in the binding energy between the outer shell and the inner shell, that energy is a quantity of kiloelectron volts, and it has to go somewhere. If it's the right magnitude, it will cause a cascade such that it issues another photon. Okay? And so an outer shell electron descending to a lower energy state creates a characteristic photon. Now, some authors will say that this characteristic cascade is part of the photoelectric effect. Maybe it is, maybe it isn't. I don't know. I don't write theoretical physics for a living. God bless, my tongue is tied today. So I treat it like the characteristic emission is a separate reaction. Okay. So photoelectric interaction is always complete absorption. Where did that chapter 13 come from? Does he revisit? Yeah, he might revisit the idea in chapter 13, the photoelectric effect. Compton scatter is very nearly the same as the photoelectric effect. There is the conservation of energy equation. So the photon that comes in pays for the binding energy of the electron, delivers the kinetic energy to the Compton electron, or in this case, in that illustration, the recoil electron. But then there's some energy left over, and so you actually get a second electromagnetic wave with a longer wavelength, less energy. So in other words, you get a scatter photon. All right, we have made it to the end of another lecture. And of course, there was about 5 videos. Um, I'll see what I can do about sharing them on the YouTube channel, but there's plenty of information and it's pretty easy to find if you want to look for that independently. All right, that's the end of the electromagnetic radiation lab, or not lab, lecture. Um, and my X-ray students should expect a quiz next week. And for the rest of you, I hope that this led to greater understanding of electromagnetic waves and their interactions with matter.